All right, let's talk about something you've probably seen 1,000 times, the periodic table. But have you ever really stopped and wondered why it has that weird kind of broken shape? Well, it's not some random accident. It's actually a code. And in the next few minutes, we're going to crack it.
I mean, seriously, look at this thing. What's the deal with the two columns floating way over on the left, and this big sunken part in the middle, then this block on the right, and don't even get me started on the two rows that look like they've been kicked out to the bottom. It looks a little haphazard, but the truth is, it's one of the most elegant, powerful information systems ever designed.
So yeah, that shape? It's not arbitrary in the slightest. It is the direct result of a handful of fundamental rules that control every single atom in the universe. We're not just going to explain it, we're going to build the table from the ground up, using nothing but those rules.
Okay, so where do we even start? Well, to crack this code, we have to go small. Super small. Right inside the atom itself. Because the secret to the periodic table's shape isn't really about the atom as a whole, it's all about how it organizes its electron.
Think of an atom like this, kind of a strange apartment building. Electrons can't just float around wherever they want. No, they have to live on specific floors, which we call shells, and in specific rooms on those floors called subshells. This whole setup, this is the atom's internal filing system, and it's the key to everything.
And here's what that address system looks like. You've got your main energy levels, the shells. And inside those, you have the subshells which get these letters, S, P, D, and F. Now here's the crucial part. Each type of subshell can only hold a certain number of electrons. S can hold 2, P holds 6, D holds 10, and F holds 14. You gotta remember those numbers. 2, 6, 10, 14. They are the entire secret.
Okay, so we've got the rooms, the shells and subshells. But how do electrons decide where to go? Is it just a total free-for-all? Nope. There's a very specific, totally predictable order they have to follow.
This rulebook has a name. It's called the Aufbau principle. It's a German word that basically means building up. And that's exactly what it tells us to do. You always fill the room with the lowest energy first, and only then do you move up to the next one. It's our instruction manual for building any element in existence.
And this diagram right here, it shows you just how simple that rulebook really is. You literally just follow the diagonal arrows. You start at 1s, then you go to 2s, then 2p, 3s, 3p. But wait, check this out. After 3p, you'd think it goes to 3d, right? Wrong. It jumps down to 4s first, then it goes back to fill in 3d. This specific path, this little detour, is the direct cause of the periodic table's unique shape.
All right, this is it. The payoff. We have the address system, we have the filling rule. Now, let's put them together and actually build the table.
Hey, remember those magic numbers I told you to keep in your head? 2, 6, 10, and 14? Well, get ready for this. The S subshell holds 2 electrons, and would you look at that? The S block of the table is exactly 2 columns wide. The P subshell holds 6 electrons, and boom, the P block is 6 columns wide. You see where this is going, right? D holds 10, so the D block is 10 columns wide. F holds 14, the F block is 14 columns wide. It's a perfect match, not a coincidence.
So what this means is, as you follow that filling path, 1s, 2s, 2p, 3s, 3p, 4s, 3d, you're not just adding electrons, you are literally taking a walk through the periodic table itself. Every time you fill an S subshell, you're in the S block. When you start filling a P subshell, you jump all the way over to the P block. The whole structure just emerges from that one simple rule.
And here it is, the big aha moment. On the left, you see our blueprint, the abstract blocks just laid out according to that filling order. And on the right, the actual periodic table. They match perfectly. The blueprint becomes the building. That strange shape we started with is just a map of electron orbitals. We cracked the code.
But okay, cracking the code is one thing. What's really cool is what the code tells us. It does more than just explain the shape. It lets us predict the behavior of elements. This structure creates these amazing, predictable patterns, or periodic trends.
First up is atomic size, or atomic radius. It's pretty straightforward, right? It's just how big an atom is, the distance from its very center to its outermost layer of electrons.
So atomic size follows 2 simple rules, but one of them is a little weird. As you go from left to right across a row, the atoms actually get smaller, which seems backwards, but as you add more positively charged protons in the nucleus, that stronger pull just sucks the negative electrons in tighter. But as you go down a column, the atoms get bigger because you're adding whole new electron shells, puffing the atom up.
And you can see it plain as day right here. Look at period 2. From lithium all the way over to neon, the size clearly shrinks. Now look down that first group, lithium, sodium, potassium. With each step down, you add a new shell, and the size just balloons. The rules hold up. So why do they get so much bigger going down? Well, it's because of something called the shielding effect. The best way to think about it is that the inner shells of electrons act like a curtain. They block the outermost electrons from feeling the full attractive pull of the positive nucleus. So the more shells you add, the thicker that curtain gets, the looser the outer electrons are held, and the larger the whole atom becomes.
Okay, so size is one pattern. Next up, let's talk about what I like to call the price of an electron. How much does it cost, in energy, to just yank one away from an atom?
Now, the technical term for this price is ionization energy. It's the minimum amount of energy you have to pay to strip one electron off a neutral atom. Some atoms give up their electrons for cheap. Others are going to charge you a really high price.
And this price follows a predictable trend that's basically the exact opposite of atomic size. It gets more expensive to remove an electron as you go from left to right, because those atoms are smaller and they're holding their electrons way tighter. And it gets cheaper as you go down a group, because the atoms are bigger and those outer electrons are shielded and held much more loosely. Bottom line, it costs a lot more to steal from a small, well-guarded atom.
And this graph shows the beautiful rhythm of that price. The peaks, the highest, most expensive ionization energies, belong to the noble gases like helium, neon, and argon. Their electron shells are full and stable, and they do not want to give up an electron. The valleys, the lowest bargain bin prices, are the alkali metals like lithium and sodium. They're super reactive because it's so cheap and easy to remove that one outer electron.
But here's where it gets even cooler. Just when you think you've got the rules down, you find an exception. The general trend is a great guide, but it's not the whole story. Sometimes, an atom's deep desire for stability can cause it to break the trend entirely. Check out this amazing example. The rule says the price to remove an electron should go up as we move from left to right, so oxygen should cost more than nitrogen. But it doesn't. It's cheaper. Why? Well, look at nitrogen's electron setup. Its p subshell has 3 electrons, which means it's exactly half filled. And it turns out that's an unusually stable and happy arrangement. Nitrogen doesn't want to lose that stability, so it charges a higher price for its electron than oxygen does, even though oxygen is further to the right. The code has hidden layers.
So the big takeaway here is that the code isn't just descriptive, it's predictive. By understanding these rules, we can predict the properties of elements that we haven't even created yet. For example, we can predict that when we finally synthesize element 119, it's going to slot right in under francium in period 8, group 1. It will be a new alkali metal, and it will probably be very large and incredibly reactive. The table already has a space waiting for it. The code tells us exactly what to expect. This isn't just a chart on a classroom wall. It's a map of the fundamental logic of our entire universe.